Greetings students. This is third online lecture of solid state physics. In this class we are going to discuss about metallic and hydrogen bonds. After this lecture you will be able to understand about how metallic bonds are formed, why the metals have high electrical and thermal conductivity, how the electrostatic energy varies with interatomic distance, the strength of metallic bond. Also, you can understand about how hydrogen bond is formed, nature of hydrogen bond, properties of metallic bond, properties of metallic and hydrogen bond, and comparison of all types of bonds. Metallic bond. Metals are characterized by high electrical conductivity and a large number of electrons which are free to move in a metal, about 1 or 2 per atom. The electrons available to move about are called conduction electrons. The valence electrons of the atom become the conduction electrons of the metal. In metallic crystals, the metallic bond arises when all of the atoms share all of the valence electrons. The valence electrons of the atoms comprising a metal are common to entire aggregate, so that a kind of gas of free electrons pervades it. The crystal is held together by the electrostatic attraction between the negative electron gas, that is in the form of an electron cloud of delocalized electrons, and the positive metal ions. The best example for a metallic crystal is sodium. The cohesion, that is the ability to remain a solid. The cohesion of the metallic crystal results from a combination of forces. So those forces are the attraction of the electron cloud for the ion cores, the mutual repulsion of the electrons, and the mutual repulsion of the ion cores. Metallic bond results from the attraction between the metal cations and the surrounding sea of delocalized electrons. Surrounding sea of delocalized electrons. Examples of metallic bond: sodium, magnesium, aluminium. So these are few examples of metallic bond. Sodium has a lone electron in its outermost orbital. Magnesium has 2 electrons in its outermost shell. Aluminium has 3 electrons in the 3s orbital. Those valence electrons are available as free electrons in the conduction band. As shown in the figure, these free electrons are delocalized electrons in the metal. These free electrons are not bound to any of the atoms, whereas all the atoms share all the valence electrons in metals. So the free electrons could pervade throughout the metal, as demonstrated in the picture. These free electrons forms sea of electrons or electron clouds in the atomic lattice. Let's discuss now on cohesive property. This is occurring by the result of combination of net forces due to the 3 electrostatic forces as discussed. The valence electrons of metal atoms move to conduction band by leaving the positive metal ions and hence forming electron clouds. These positive metal ion cores attract the surrounding electron clouds that contributes to the binding energy. This attraction is mutual. At the same time, there will be mutual repulsion among electrons when the free electrons are coming closer to each other. On the other hand, when the positive ions are attracted by electronic clouds mutually, the positive ions come closer to each other and gets mutually repelled by each other. This effect is because of the overlapping in electronic orbitals of the metal ions. When more electrons are trying to enter into the ionic boundary, Only the permissible electrons can occupy the valence orbital and the remaining gets repelled according to the Pauli's exclusion principle. This effect is increasing the potential energy. This picture indicates electrostatic or cohesive energy variations with respect to internuclear distance. As evidenced from the plot, the net potential energy is drawn under the influence of ion repulsion term, free electron repulsion, and metal ion free electron attraction. The dark blue line represents net energy here. As indicated, the upper and lower dotted positive slopey curve are representing the ion repulsion and free electron repulsion respectively. When the metal ions are very close, the outer orbitals are overlapping. As discussed earlier, the ions are repulsive, which increases potential energy. In addition to that, when the free electrons are attracted by the metal ion, they come closer and there will be electrostatic repulsion, which also contributing the potential energy. So metal ion repulsion and free electron repulsion are dominating in this region. However, the attraction between metal ion and free electrons exists, which dominates the potential energy when the distance slightly increases. When the distance between the metal ions slightly increases, these are dominating. Hence, when the distance between the metal ions increases, the potential energy gradually decreases. At a certain distance between the metal ions, the attractive interaction of metal ion and free electrons dominate, which pulls down the net energy to negative region as shown in the picture. When the distance increases, the electrostatic attraction gradually increases and the electrostatic energy due to the repulsion terms gradually decreases. At a certain distance, let us say R0, the metallic bond is very stable, which is known as equilibrium distance. At equilibrium distance, the ion repulsion term reaches 0. But still, the free electron repulsion is there. Upon further splitting of metal ions up to certain distance, there will be attraction term, and beyond large separations, the attraction term is negligible, and hence the net potential energy will be decreasing abruptly in this region as shown in this plot. Metallic bond is formed by the partial sharing of valence electrons by the neighboring atoms. Unlike the case of covalent bond, the sharing in metallic bond is not localized. In the case of covalent bond, as we know, the electrons are shared between the atoms, whereas in metallic bond, all the valence electrons are shared by all of the atoms. Hence, metallic bond may also be considered as delocalized or unsaturated covalent bond. As proposed by Drude, the atoms in metals contribute their valence electrons to form a common pool of electrons which has freedom to move anywhere in the framework of positive ion cores. This common pool of electrons is also known as the free electron cloud or gas and acts like a mobile glue to bind all the ion cores together through electrostatic attraction. The bond so formed is called the metallic bond. In this type of bonding, the atoms can share the required number of electrons with their neighbors through the common pool to complete their valence band. Due to delocalized nature of valence electrons, the metallic bond is much less directional than covalent bond. The metallic bond is weaker than ionic or covalent bond. The binding energy ranges from 1 to 5 electron volt per bond. However, we can say the metallic bond is stronger than van der Waals bond. The melting and boiling points of metallic solids are lower than ionic or covalent solids. Also, these solids have high ductility and malleability, high electrical and thermal conductivities, and high optical reflection and absorption coefficients. Ductility and malleability are the ability of a material to deform under tensile stress and compressive stress respectively. Metals are good conductors of electricity and heat because the free electrons carry charge and heat through the metal. The free electrons allow the metal atoms to slide over each other, so metals are flexible. Vacant p and d orbitals in metals' outer energy levels overlap and allow outer electrons to move freely throughout the metal. Valence electrons do not belong to any one atom. The following are the characteristics of metal crystals. The presence of free electrons accounts for the high electrical and thermal conductivities of metals as already discussed. The high electrical conductivity of metals is in turn responsible for their high optical reflection and absorption coefficients. The other characteristic properties of metals are their ductility and metallic luster. Since the metallic bonds are not localized between adjacent atoms, the atoms of a metal can be rearranged in a position without returning to the crystal. This explains ductility of metals. When light shines on a metal, the free electrons oscillate under the electromagnetic field of the incident light and become sources of light. This gives the metal its surface luster. Metallic bonds are weaker than ionic and covalent bonds, as already discussed. So those are the properties of metallic bond. And now let us move on to the next topic, hydrogen bonding. Since neutral hydrogen has only one electron, it should form a covalent bond with only one other atom. It is known, however, that under certain conditions, an atom of hydrogen is attracted by rather strong forces of two atoms, thus forming a hydrogen bond between them with a bond energy of the order of 0.1 electron volt. So why two atoms? It's because hydrogen is already in covalent bond with one atom, and the remaining, the other side, it could form a hydrogen bond. So one side covalent and the other side hydrogen bond. So that's why it is under the strong forces of two atoms. Hydrogen bond is formed under certain conditions when a single hydrogen atom appears to be bonded to two distinct electronegative atoms. The configuration is represented as X, H with dotted lines Y, where X is called donor, that means donor of hydrogen bond, and while Y is called acceptor, that means acceptor of hydrogen bond. The weaker of the two bonds shown by dotted line is the hydrogen bond, while the other shown by a full line is a strong covalent bond. So the examples are water, H2O, ammonia, HF are examples of hydrogen bonded crystals. When a covalent bond is formed between a hydrogen atom and a highly electronegative atom, such as an atom of oxygen, fluorine, chlorine, etc., the shared electron pair gets attracted more towards the electronegative atom than the hydrogen atom. Thus, the electronegative atom acquires a slight negative charge and the hydrogen atom acquires an equal amount of positive charge. The molecule so formed is said to be polarized and behaves like a permanent dipole. A number of such dipoles get attracted to one another due to the Coulombic force of attraction. This type of interaction between the oppositely charged ends of permanently polarized molecules, each containing a hydrogen atom, is called the hydrogen bond. So about the hydrogen bond, we are also going to discuss more with schematic pictures in the next few slides. So a special significance is attached to hydrogen atom because it can be regarded simply as a proton fixed to one end of a covalent bond and the positive charge of which is not shielded by the surrounding electrons, because hydrogen has only one electron. So the positive charge of the nucleus is not shielded by the surrounding electrons. It's because hydrogen has only one electron, which is already shared with other atom in the covalent bond. So the shared electron is mostly spending time with the electronegative atom than the hydrogen. So the hydrogen will be more electropositive, which needs an electron to shield the positive charge of proton at the nucleus. It needs equal electron sharing. So this is not the case with other atoms participating in a covalent bond. Their positive charges are shielded by the outer electrons, which weaken the attraction of the positive nuclear charge with the negative ends of other polarized molecules. So even though polarized molecules are formed in other elements, their positive charges are shielded by outer electrons. So the electropositive momentary ion formed may not be strong as hydrogen. Therefore, the positively charged hydrogen atom can interact more strongly with the negative ends of other molecules, so as compared to any other positively charged atom. In the case of other elements, there are more nuclear surrounding electrons, whereas in hydrogen atom, as we know, only one electron is there. So materials exhibiting hydrogen bonding possess high melting and boiling points compared with molecular solids. The hydrogen bond plays an important role in the formation of ice and water. The binding energy of water or ice is about 0.5 electron volt. So hydrogen bonding is responsible for the striking physical properties of water and ice. In the absence of hydrogen bonding, the boiling point of water at atmospheric pressure would have been minus 80 degrees Celsius instead of 100 degrees Celsius. Since a hydrogen bond is formed between oppositely charged ends of two permanent dipoles, it is directional in character. Here is the example for hydrogen bonding between water molecules. Oxygen is sharing two electrons of its valence electrons with two hydrogen atoms respectively through covalent bonds. The existence of other two lone pair electrons add electronegativity to the oxygen atom. Due to the strong electronegativity, oxygen valence orbit attracts the both electrons in addition to the electrons under sharing with each hydrogen atom. Hence, hydrogen atom gains electropositive nature. This electropositive hydrogen seeks an electron to shield its proton. On the other side, the oxygen atom is with excess lone pair electrons with strong electronegativity. The electropositive hydrogen undergoes hydrogen bonding with electronegative oxygen. So the hydrogen gets attracted by two oxygen atoms simultaneously. Hydrogen electron sharing with the oxygen atom forms a covalent bond which is very strong, and on the other side the hydrogen makes a bond with electronegative oxygen through hydrogen bond which is also strong but weaker than covalent bond. So the water molecules gains strong hydrogen bonding. These bonds, that means the hydrogen bonds, are stronger than van der Waals bonds but weaker than ionic or covalent bonds. The hydrogen bond is an important part of the interaction between water molecules and is responsible together with the electrostatic attraction of the electric dipole moments for the striking physical properties of water and ice. So because of the hydrogen bond, the melting point of water is 100 degrees Celsius, otherwise it would have been minus 80 degrees Celsius. So it is important in certain ferroelectric crystals and in DNA. In this picture, interaction between ammonia and the water molecules is shown. The nitrogen atom in ammonia is bonding with three hydrogen atoms through covalent bond. So three valence electrons are involved in covalent bond and one lone pair electron is left alone. Hence, nitrogen gains electronegativity. As already discussed, this strong electronegativity creates polar covalent bond with hydrogen and hence permanent dipoles are formed. On the other hand, all the three hydrogen atoms are with strong electropositive nature. The lone pair electrons of oxygen atoms in water molecules make hydrogen bonding with all these hydrogen atoms. So here, nitrogen acts H bond, that means hydrogen bond donor, and oxygen acts as hydrogen bond acceptor. In a similar manner, the oxygen is in covalent bond with two hydrogen atoms and those two electropositive hydrogen atoms make hydrogen bonding with nitrogen. Here oxygen acts as hydrogen bond donor and nitrogen acts as hydrogen bond acceptor. In this slide, we have a comparison chart of all the types of bonds in solids. So the types of bonds are ionic, covalent, molecular and metallic bonds. The bond formation in ionic is by electric attraction or electrostatic attraction and covalent by shared electrons. Molecular by van der Waals forces, metallic by electron gas or free electron cloud. And the properties of ionic bond or ionic bonded solids are hard. These ionic bonded solids are hard, high melting points, may be soluble in polar liquids such as water, and these are electrical insulators but conductors in solution. That means in solution, the ionic crystals are in dissociated form with cations and anions. So these ions could give conduction under electric field. In the some examples are sodium chloride. So its cohesive energy is 3.28 electron volt per atom. In the case of covalent bond, the properties of the covalent bonded solids, these solids are very hard and these are having very high melting points, insoluble in nearly all liquids, semiconductors, these are semiconductors, and except diamond, which is an insulator. So example is diamond, and here the cohesive energy is 7.4 electron volt per atom. And in the case of molecular bond, that means the van der Waals forces, the properties of these van der Waals crystals, molecular crystals, these are very soft and low melting and boiling points, soluble in liquids, covalent liquids, electrical insulators. Examples is methane, and its cohesive energy is very less, it is 0.1 electron volt. It is the lowest among all the types of bonds. And the next one is the metallic bond, and in the case of metallic bonded solids, the properties are ductile and malleability, metallic luster, high electrical and thermal conductivity. These are the properties of metallic bonded solids. And example is sodium, and its cohesive energy is 1.1 electron volt per atom. So in the case of metallic bonded solids, the cohesive energy is less than ionic and covalent but higher than the van der Waals forces. The cohesive energy is the work needed to remove an atom or molecule from the crystal, and so indicates the strength of the bonds holding it in place. So that's all about the metallic and hydrogen bond. In this lecture we have discussed on how metallic bonds are formed, the potential energy variations with interatomic distance, hydrogen bond formation with water and ammonia, examples, and comparison of all types of bonds in solids. So students, hope you would have understood the concepts. In the forthcoming lectures, we are going to discuss on atomic radii and elastic strains. And these are the references reference books used to prepare this presentation. The book references are Modern Physics by R. Murugeshan, Kritika Sivaprakash, and Solid State Physics by R. K. Puri, V. K. Babar. These are the reference books. So students, stay at home, wear mask and sanitize your hands when you are going out. Stay safe. Thank you.